Hello, good morning, everyone. We are going to do, hold on. Hello, everyone. We're going to do a little bit of a warm up today. We'll start with a warm up here. Typical question people always ask me is, Mr. Who, what did you do over Thanksgiving? So I'm going to tell you what happened because this is definitely a true story. This definitely happened over Thanksgiving. So over Thanksgiving, so I had an apple pie and then I had a pumpkin pie. And then as a true physics teacher, I decided to play the game, which pie hits the ground first with myself because I don't have any friends. So if I throw the apple pie horizontally, so I'm throwing it horizontally with a velocity of 10 meters per second. At the exact same time, I drop the pumpkin pie vertically to the ground. Which pie hits the ground first, right? So I'm throwing one horizontally, and then the other one I'm dropping at the exact same time, dropping one vertically, throwing one horizontally. Which pie hits the ground first, and then respond with, and so that's for the first question. And then for the second question, just respond with your favorite type of pie. Shout out to my banana pies. Banana pies are really good. Um, yeah, sorry. Ooh, key lime. That is a bold one. I respect that. Key lime pie is also very, very, very good. Um, Huge fan of key lime pie. That's very, very, very good. Um, Great tasting pie. Rice pie. Wow, I've never had rice pie before. That sounds actually, I don't know how I feel about that. I love rice. I don't know how I feel about rice. I don't even know if that's a real thing, but if you say it's a real thing, Galen, I believe you. I'm down to try some rice pie sometime. Um, Apple pie. Apple pie is so good. I know, like apple pie is kind of like a what's the word? A pleb thing to like, but I'm a huge fan of apple pie myself. If I had to pick one pie, I'd go with apple pie. Um, Pecan pie is also really good, Serena. Good choice. Cherry pie. Cherry pie is also really good. Um, and are there any pies I don't like? I don't know what pies I don't like. Good question. We'll see. We'll see. So we got a few answers so far. We got a bunch of good answers so far. Let's take another couple of minutes to see if we can figure out which, if we have any ideas of which pie hits the ground first. And then you can always feel free to share your favorite type of pie. Um, Actually, I didn't really have any pie for Thanksgiving. This is me living my dream vicariously through all of you. So I'm definitely down for some pie. And then we will get started with our what we are going to be talking about today. So today we're not actually going to be talking about pie, unfortunately. Maybe next time we'll talk a little bit more about pie. But we will instead talk about some other very fun things, which involves projectile motion. So here's what we're doing today. Today we're going to do the last bit of apple pie because it probably weighs more. Ooh, actually, that's also really interesting too. We'll get into a little bit more of the nuances of throwing pies. Um, but for now, we're going to take a look at two-dimensional projectile motion. Um, yeah, two-dimensional projectile motion, which is going to be the last unit-ish thing that we're going to be doing this semester. Um, so Okay, so let's talk a little bit about projectile motion. You probably have seen, probably have some idea what projectile motion is. Pumpkin pie, you have it on your birthday? Ah, lucky, lucky, Sam. I wish I had pumpkin pie on my birthday. I'm so jealous. That sounds really good. Great birthday tradition. Um, so you probably have seen some sort of projectile motion before. If you've ever thrown something at your siblings or thrown something at your friends or thrown a paper ball or thrown anything, it all undergoes some sort of projectile motion. So any sort of projectile is an object that moves in a curved path due to gravity. So in a sense, it's in free fall, right? So what happens is an object goes up and then eventually goes down due to gravity. And then because of this, it ends up moving in a curved path due to gravity. So any sort of projectile that is in projectile motion, they will undergo acceleration, and they will go under acceleration in the vertical direction due to gravity. Right, gravity accelerates all things vertical in the vertical direction. So projectiles will undergo acceleration in the vertical direction due to gravity. Gravity is, as you remember, 9.8 meters per second squared, and that is how much gravity accelerates your projectile every second. So in general, well, this is generally when we're working in this class, and in general, we sort of when we talk about projectiles, we generally assume that they don't have any sort of horizontal acceleration. So the idea is once a projectile is shot or launched or whatever, it's not really accelerating horizontally anymore. And so because it's not accelerating horizontally, there is not going to be any sort of change in the horizontal velocity. The initial horizontal velocity will generally stay the same throughout the trajectory. Um, Again, this is sort of making a few assumptions here. We're assuming that we're ignoring air resistance. Again, we're assuming that, but in general, this is sort of what we're looking at. The only acceleration is due to gravity, and that's vertical, and there's no real any sort of horizontal acceleration. So when we talk a little more about projectile motion, what's important is we want to make sure we sort of split up our projectile motion into horizontal and vertical components. Something we've actually done a little bit before. What's very important is that horizontal and vertical components, your x and y, they are completely independent of each other, right? They are completely perpendicular, which means that what happens vertically has no impact on your horizontal motion, and vice versa, right? So what happens in your horizontal motion, what happens to your x has no effect on your y at all. So what happens in x stays in x, what happens in y stays in y. And this is why gravity only affects your vertical motion, right? So what can be kind of tricky is when you try to identify your horizontal acceleration, you're like, I don't know how fast I'm accelerating horizontally. Well, the answer is your horizontal acceleration is not gravity. It could be something else, but it's never gravity because gravity only affects your vertical motion, does not affect your horizontal motion. And this is why the pies in the warm up actually hit the ground at the exact same time. There's also a couple of other nuances with that, which we'll talk about next semester. But the thing is, gravity is the only thing affecting the vertical motion of both pies. So throwing a pie horizontally has no impact on whether or not it hits the ground first. So both pies hit the ground at the exact same time because they both had the exact same vertical acceleration, which is gravity, and they all have the same initial vertical velocity, which is 0. So when we tackle a projectile problem, we will break up the motion into two components, x and y. So what happens in x stays in x. So this will sort of include any sort of horizontal positions, any sort of horizontal velocities, any sort of horizontal accelerations. And what happens in y stays in y. This includes any sort of horizontal position. This says horizontal, it should say vertical. This includes any sort of vertical positions, vertical velocities, and vertical accelerations. Yeah, but what happens in x stays in x, what happens in y stays in y, and they don't never affect each other. And sometimes both components, they may share the same time. I just want to be a little careful with this. They both may share the same times depending on the scenario, depending on how you set it up. So they may share the same time, but that's not guaranteed either. So be very careful with that. Yeah, so to reiterate, very, very, very important. If you're going to remember one thing, horizontal and vertical are independent of each other. They do not affect each other. You work in horizontal, you work in vertical, you never mix the two. They're like ammonia and bleach. They work great on their own, and then when you mix them together, everybody dies. So don't mix ammonia and bleach, chemistry lesson, and don't mix horizontal and vertical components, because if you do, you will die, which is very important. Okay, so let's talk a little bit about solving problems. So um, so we've actually already done a projectile motion problem previously. So we're going to take a look at, we're going to sort of revisit the ejection seat problem. So before you start complaining that I never teach you anything and you don't know how to do a projectile motion problem, we actually already did one in Mario Kart Part 3. This is question 5D. This is actually a full-fledged projectile motion problem that you've already done. So you're not allowed to complain that I never teach you anything because you already did it. And then this is a shout out to the Mythbusters episode about ejection seats. RIP Grant Imahara. He's a great guy, and he died, I think, this year. Very unfortunate. But then the Mythbusters episode is very good about ejection seats. So now we're going to revisit the ejection seat problem. So for this problem here, for the ejection seat problem, we're going to take a look at changing some variables up. Okay, so in the previous problem here, if you remember, what had sort of happened is you had an initial horizontal velocity and then you had some other stuff. Um, so, and then you try to figure out basically how far the ejection seat lands horizontally. Um, it's going to be the same idea here. We're just going to change up a couple of things for this particular problem. So for this problem, what I want you to think about is that for this problem we're going to examine today is that the car and the ejection seat are both initially stationary. The car never actually moves, and the car is just irrelevant for this problem. So just ignore the car. The ejection seat is initially stationary. And then what happens is the ejection seat, it launches you with a velocity of 40 meters per second at a 45-degree angle. So this is the first time we're using trig in physics, and we will take a look at why this is important. So in this problem here, the ejection seat, sort of similar to the picture on the diagram here, the ejection seat launches you vertically, at an angle of 45 degrees with an initial velocity of 40 meters per second. So let's try to figure out a few things here. Let's first try to figure out what our initial vertical velocity is. Let's then figure out our initial horizontal velocity, and then what are your vertical and horizontal accelerations. So your vertical velocity and your horizontal velocities in this problem are not given, right? But you can figure them out. And I want you to see if you can try to figure it out here. So very simple. You're given an ejection seat that launches you with a velocity of 40 meters per second at a 45-degree angle. So I want you to figure out what is your initial vertical velocity, what is your initial horizontal velocity, and then what are your vertical and horizontal accelerations. So we'll take a few minutes, and then whenever you're ready, just put your answer in the Zoom chat, and then we will see what we can get. So a key hint here is that you are given a diagonal velocity. So it'll be very helpful to use, trig to try to break it down into, decompose it, if you will, into vertical and horizontal components, right? So in physics or in anything in general, when you're given something that's sort of diagonal, you want to break it down in terms of x and y. So this is where you use a lot of trig here to try to break down a diagonal into horizontal and vertical velocity. So we got a couple of good answers so far. What is it gonna be? Another minute or two. And then if you can try to figure out our vertical and horizontal accelerations, that would also be pretty dope as well. I think that actually should be pretty straightforward. And I know you can't see the whiteboard. I know. I'm just waiting for people to give you another chance to finish. Is there a bird? I'm hearing a bird too, but it's not coming from me. Uh, um, I don't have a bird here, fortunately. Okay, so I think we're sort of on the right track here. I will let you try to, if you haven't finished it, it's okay, you can take some more time. I'm gonna start taking a look at this. Okay, so this right here is a huge big brain moment right here. So this is why trig is super important. So what we have here is we have a diagonal velocity. We have 40 meters per second in diagonal direction, and we have that this angle here is 45 degrees, right? So this in itself, the 40 meters per second, is kind of useless. It doesn't really help us at all. We need to know the vertical velocity, and we need to know the horizontal velocity. So to do this, we can recognize that this is a 40, 45, 45, 45, 90 triangle. So what we're going to do is we're going to try to figure out the vertical velocity and then and then the horizontal velocity. Okay. So if you know your trig, right, the vertical component here is the hypotenuse times the sine of 45. So what we're going to have is 40 sine 45. And then for the horizontal velocity, it's going to be 40 cosine of 45. This is just 40 root 2 over 2. And this is 28.28 meters per second. And then the cosine is the exact same thing. This is also 28 meters per second. All right. So now we know, based on just one angle and one diagonal velocity, we know the horizontal and the vertical velocities. Very, very important. Okay, and then so now we can figure out the horizontal and vertical accelerations. So remember that vertically, this problem, once you are launched, there's nothing accelerating you anymore other than gravity. So your vertical acceleration is 9.8 meters per second squared. And then your horizontal acceleration, once you're launched, again, there's nothing pushing you horizontally. Acceleration is just basically whether or not something is pushing or pulling you. We are moving, but there's nothing pushing or pulling us. So horizontal acceleration is just 0. And so this is our acceleration, our velocity. Okay. So from here, we can then figure out basically how far we travel. We can figure out how far we travel, how long it takes to hit the vertex. But I will leave that as a fun little exercise for you because we will be doing that quite a bit later today. Okay, so does anyone have any questions for me? I don't think this should be too new for people, but again, I could be wrong. Does anyone have any questions for me? Okay, all righty. So, okay, so what we're gonna do today is we're gonna start our last assignment here. I called it World War II projectile motion. I am a big history person. I love history. And so I spent a lot of time reading about boring stuff in history. Well, I think it's interesting. So we're going to take a look at some World War II projectile motion. This is for those of you who are still on the boat that physics is not useful. You will see why physics is useful. Okay, so on Canvas, there's an assignment called World War II projectile motion. I have it on the screen right here. I will also link it in the chat so you can open it up easily. And let me know if it doesn't work. It should be shared. Oh no, it wasn't shared. Hold on. There we go. Okay. Oh no. You don't. I don't want you to be an editor. That's not good. Okay. That's good. Okay. So so we're gonna take a look a little bit at some history. Yeah. Okay. So this will be kind of, I will do a little bit of a visual here in a second, but I'm going to do a little bit of a history lesson. So for most of history, most casualties, in other words, people who died or who were wounded in war, most casualties were actually not due to any sort of violence. It was actually due to disease. So disease killed pretty much most people up until World War I. I think World War I think was the first war where more people were killed by violence than they were killed by disease. So disease is super nasty. In World War I though, World War I was the first time where a lot of new things happened. And most casualties, in other words, most people who were killed or wounded in World War I was actually due to artillery. And this is true in World War II as well. So artillery, if you don't know what artillery is, and artillery is basically like a giant cannon, sort of. But I have a picture right now, as you can see. So this is what artillery looks like here. You have sort of like this, basically this cannon thing that shoots a large projectile. This is sort of what it used to look like in World War I. It's a little bit more advanced nowadays. But basically, it's just basically just like a large cannon that just shoots like a shell, an explosive, and then hits the ground. And it's very, very, very dangerous, very deadly. So in World War II, the vast majority of casualties were caused by artillery. So in the European theater, 65% of casualties were due to artillery, which is a lot. And in the Pacific theater, which you would think would be a little bit more, I don't know, a little bit different. It was still 47% of casualties were due to artillery. And so because of this, and the reason why it was so deadly is because artillery, you have some, modern artillery is very accurate. There's a lot of firepower, there's a lot of explosives, and they also have very, very long range. So what happens is because of this, you can pretty much die or get wounded without ever having seen the opposing forces. So, in previous wars, you would actually see the opposition. In modern war, you probably won't even ever see the person. You'll just get hit by artillery and then you'll very unfortunately face that. So one of the most important roles of artillery is that something we call defensive support. So basically what happens is if there's a front unit of soldiers under attack, they're going to call for defensive support from an artillery battery. So they're just like, we need artillery here. There's enemy closing in. So once an artillery battery receives instructions from, they're going to have to calculate the range, the altitude, and the trajectory at which to fire the batteries. So our goal for this assignment is to create equations that will allow us to provide supporting fire for basically soldiers under attack. So what's going to happen is after you create equations, I will give you different variables, and you're going to try to figure out what angle you need to fire the battery at in order to hit the target. So by what it means by three different variables, I will give you I won't give you a distance. I will give you a velocity, and then I will give you a range. In other words, how far the target is, and then your goal is to figure out what angle you need to fire the battery at. So when you tell me an angle, I will basically tell you whether or not you hit, which in other words, whether or not you successfully hit your target, or I will say miss, and then in which case you miss your target, and then you're going to have to try to make some adjustments to your formula until you're ready for another test. So at the same time, you're going to try to record how long it takes to figure out an accurate angle. So this will happen after you can take as much time as you need to create your equation. But once you're ready to have your first attempt, we're going to start measuring your response time. This is not graded. I just think it'll just be for fun to see how long it takes for you to dial in other words, an accurate shot. The reason why this is kind of interesting is because in World War II, the Americans did get it down to 30 seconds at the fastest. So 30 seconds to calculate the angle you need to fire a shot at, and this is including wind and altitude and humidity and temperature and so a lot of other things. So they could get it down in 30 seconds in World War II, and this is without any calculators or phones or Google Sheets or Discord or Zoom, right? They could get it down in 30 seconds with nothing more than pen and paper. So here's what we're going to do today and tomorrow, or not tomorrow, Thursday. So we're going to first initially prepare to provide artillery fire for a frontline unit at the same elevation as you. So basically, for these problems, you're going to assume that the target is at the same elevation as you. So your goal here is to write a general equation that calculates the angle you need to fire an artillery battery in order to hit a target that is X meters away. The velocity at which an artillery shell is fired is V naught. It will be given to you. Yeah, it will be given to you. But for now, just use V naught. So when your group is ready for equations, let me know. I don't think we'll get to this today. I'm going to give you all of today to figure it out. So yeah, your goal is basically write an equation that figures out how much of an angle you need to fire an artillery battery in order to hit a target. And then the rest of this occurs whenever you're ready to start firing projectiles. Imagining projectiles, but I don't think we'll get to that. Does anyone have any questions? Okay, so before we get started, I will just give you a visual so that way you can sort of a visual idea of what's going on here, so that way you aren't too confused. So basically, okay, so basically in this sort of problem, you have a V naught, you have an initial velocity, and you have an angle, and then you have distance. So I will give you a distance here. I will give you an I will give you a distance here. I will give you a velocity here. And then I will let you figure out the angle. So what happens is in projectile, you shoot something, it goes up and it comes down. And so you know your velocity and you know your final distance, and then you don't know anything else. Anything else you're gonna have to try to figure out. And your goal is to write an equation that has theta in it. So you don't need an exact, like, you don't need to have like an equation that's like, where that is theta is equal to, some other nasty stuff, right? As long as it has like, sine theta or something is times this. As long as you have something like this, that's good enough. Is if you have theta like this, you can have like a tangent inverse or sine inverse or whatever, which might be a little bit nasty. You can just leave it in this in like a sine. But I will let you figure it out. So yeah, you're going to derive an equation to figure out the angle. Okay, so you don't have any questions. I'm going to let you get started. The assignment is on Canvas, and then I will let you get started, and we'll take the rest of the period today to see where we are. And then yeah, and let me know if your group has any questions. You can always PM me if you have a question for me, if your group has. But yeah, let's get started. Okay, so a couple of things are that I just want to make clear. So this problem does not test your mathematical ability in terms of how much random trig variables or trig identities you know. It's actually pretty simple algebraically. You could probably do it in a few lines, nothing crazy. So if you're like doing this like crazy like page long derivation, that's way too much. It's actually not too bad mathematically. That being said, it's also not super simple either. So if you're like, if you're doing it super simply, that may not be correct either, because it requires a lot of understanding a lot of the phenomenon going on here. So it's not super simple. It's also not super nasty either. So that's one thing to help guide you along here. Okay, everyone, we got a minute left, so I'm gonna wrap up now. So no homework today because, well, no homework, other than to submit anything you haven't submitted yet or any revisions you want submitted. Um, and then, submit revisions or anything you haven't submitted. And then you can try to take a stab at this if you want. But we'll have more time to work on it, on Thursday. So don't worry too much about it. And then in terms of, any last assignments, I would try to get them in before finals week, as a way of, making it so finals week is easier for you, but that's what I would recommend. Other than that, I will see you all on Thursday. Yeah. So have a good one.
Thank you.
Thank you.